Okay, this video is going to go over the first law of thermodynamics. We're going to do an energy balance for a closed system. The first law of thermodynamics states that energy is conserved. If we look at all of the concepts that we've learned so far, basically we can sum up the first law of thermodynamics as saying the change in the amount of energy contained in a system during some time interval is equal to the net amount of energy transferred in across the boundary by heat minus the net amount of energy transferred out by work. If we want to put that in symbols, we have our change in energy, or E2 minus E1, is equal to our heat transfer in minus our work. So this is our energy balance. And our change in energy is our change in kinetic plus our change in potential plus our change in internal. It's going to be equal to our heat minus our work. This is a big important equation. It's the energy balance for closed system. We're going to use it quite often. We also have the time rate version where the rate of energy change with time is equal to our heat transfer rate minus our power. And again, that's going to be your change in kinetic energy plus your change in potential energy plus your change in internal energy. And again, what those symbols are saying is that the time rate of change of energy within a system at time t is going to be equal to the net rate at which energy is transferred in by heat minus the net rate at which energy is transferred out by work. Honestly, the best way to learn how to use the energy balance is to do an example. So we have 4/10 of a kilogram of a certain gas contained in a piston cylinder assembly. The gas undergoes a process for which the pressure volume relationship is PV to 1.5 is equal a constant. We have the initial pressure, which is 3 bar. We have the final volume. We have the initial volume and the final volume. We want to find the change in internal energy of the gas. Noting that there are no significant changes in kinetic or potential energy, we're going to also determine the heat transfer for the process. So we have gas in a piston cylinder assembly where PV to the 1.5 equals a constant. It's undergoing a process where it expands from state 1 to state 2 from 3 bar and 0.1 meters to 0.2 meters and an unknown pressure. So we'll write down our energy balance. So we have the change in kinetic plus the change in potential plus the change in internal is equal to our heat minus our work. So we're trying to solve for the heat transfer. Well, the problem says there's no kinetic and there's no potential. So Q, our heat transfer, is going to be equal to our change in internal energy plus our work. It's a polytropic process, so our work is equal to P2 V2 minus P1 V1 over 1 minus N. And we need P2. So P2 is equal to P1 times V1 over V2 to the N, which is 3 bar times 0.1 over 0.2 to the 1.5, which is equal to 1.06 bar. So our work is equal to 1.06 bar times 0.2 meters cubed minus 3 bar times 0.1 meters cubed divided by 1 minus 1.5. I'm going to correct our units, 10 to the 5 newtons per meter squared for 1 bar, and 1 kilojoule is 10 to the 3 newton meters. We're going to get that our work is equal to 17.6 kilojoules. So Q is going to be equal to our mass times our change in specific internal energy plus our work, which is our 4/10 of a kilogram, times our minus 55 kilojoules per kilogram that was given in the problem, plus our 17.6 kilojoules, which equals minus 4.4 kilojoules. And since Q is negative, it is heat out. It's heat out of the system. There's an interesting example in the textbook as well as in my notes about what happens if you consider alternative systems when defining your problem and how it affects how you solve your problems. We'll go over it in class. We're going to do one last quick problem. Again, there's a lot of problems in here, and I will do some of them in class. Feel free to ask me any questions. We're going to look at this one that says air expands adiabatically in a piston cylinder assembly from an initial state where P1 is equal to 100 psi and the specific volume is equal to 3.704 cubic feet per pound, and the temperature is 100 degrees Rankine, to a final state with a pressure of 50 psi. The process is polytropic with N equals 1.4. The change in specific internal energy in BTUs per pound can be expressed in terms of a temperature change. We're asked to determine the final temperature. So we write down our energy balance. We're going to have that our change in kinetic plus our change in potential plus our change in internal equals our heat minus our work. There's no change in kinetic and there's no change in potential energy as stated in the problem. It also says that air expands adiabatically, which means that there's no heat transfer. So we have that our specific energy change is equal to our work per unit mass, which is equal to 0.171 T2 minus T1. So in order to find our final temperature, we have to find our work. Again, it is a polytropic process, so our work, in this case per unit mass, is equal to P2 V2 minus P1 V1 over 1 minus N, where we need V2. Well, from our polytropic relationship, we have V2 is equal to P1 over P2 to 1 over 1.4 times V1, which is 3.704 feet squared per pound, times 100 over 50, so 1 over 1.4, which is 0.677 cubic feet per pound. So our work per unit mass is 50 psi times 6.077 feet cubed per pound minus 100 psi times 3.704 feet cubed per pound divided by 1 minus 1.4. To fix the units, there's 144 inches squared per foot squared, and 1 BTU is 778 foot-pounds. So our work per unit mass is equal to 30.794 BTUs per pound. So we're going to solve the energy balance for T2. We get T2 is equal to minus our work over per unit mass over 0.717 plus T1, which equals minus 30.792 BTU per pound over 0.717, and the units of this are BTU per pound degree Rankine plus 1000 degrees Rankine gives me that T2 is equal to 889.9 degrees Rankine. In our next lecture, we're going to go over power cycles, refrigeration cycles, and heat pump cycles, which will bring us to the end of chapter 2.